All right, hi everyone. Today we're gonna do something that only the honors kids get to learn, and that's some special light stuff. So let's take a look. First, I just want to review the photoelectric effect, and basically, what it is when light hits a metal and the frequency is strong enough, then electrons will be released. So just thinking about our ground state here, going to excited state. This is what normally happens, but if there's a wave of energy that's so strong, then it'll actually send the electron flying off of the atom. And that's what's going on in the photoelectric effect. So this just shows that light behaves like a particle in addition to behaving like a wave, which we discussed. Okay, in this class you'll also learn these light equations. So there's two in particular. Here E equals hv, where E is energy, which is going to be expressed in joules, the letter J. H is Planck's constant, which is 6.626 times 10 to the negative 34 joules per second. And then V is frequency, which is in the units s to the minus 1, which is the same as 1 over seconds, or hertz. And then we also have another equation relating wavelength, the speed of light, and frequency. So again, V is frequency. C is the speed of light, 3 times 10 to the 8th meters per second. And then we have wavelength, which is in meters. So just to review, remember frequency is how often a wave repeats a cycle. And then a wavelength would be the distance from the bottom of one wave to another. So this is your wavelength. Okay, so we're going to do a couple practice problems together. What is the frequency of a wave with a wavelength of 6.06 times 10 to the minus 7 meters? So again, you're going to need a scientific calculator to do these problems. So we are just going to plug in the numbers we know. C is going to be 3 times 10 to the 8th meters per second. I'm going to plug in the wavelength. So that Greek symbol on the bottom there, that's the symbol for wavelength. Okay. And if you punch this into your calculator correctly, you are going to get 4.95 times 10 to the 14th, and that's going to be in s to the minus 1. So the meters cancel out and we're left with seconds in the denominator. Notice I kept 3 significant figures in my final answer because that's what I was given. Okay, what is the energy content? How much energy would this wave of light or quantum of light have? So again, we're just going to plug in our numbers. Planck's constant is this times 10 to the negative 34, and the units were joules per second. And then we've got this number, 4.95. So here these seconds will actually cancel out, and if we punch that in our calculators, we get 3.28 times 10 to the negative 19 joules. So energy is expressed in joules. Okay, and lastly, we'll have a problem here. What if we are given the frequency, and here we're solving for wavelength? So it's pretty straightforward. We're just going to switch these two positions. Basically, we're dividing both sides by frequency and multiplying both sides by wavelength. So our new equation looks like this. And that's how we can solve for wavelength. Now it's just a matter of plugging in the numbers. So the speed of light, 3 times 10 to the 8th meters per second, over the frequency here, I'm going to change this to seconds so that it's consistent. Since these seconds are both in the denominator, they're just going to cancel out. And then my final answer is going to be, looks like 7.0 times 10 to the minus 123 7 meters. And that's my final wavelength. Okay. So play around with your calculator. You may need to put this part in parentheses, but that's how you do these light problems. It's just a little bit of algebra using numbers with exponents here.